Okay, this is our final rule here. This is the chain rule, and it's going to allow us to take the derivative of the composition of two functions. And so I'll write out the chain rule like this. So let's say I want to take the derivative of f of g of x. Okay, so we basically have an outside function, which is f of x. It's like you have f of whatever, and inside f of x you have g of x, right? And so what you're going to do is you're going to take the derivative of the outside function here, evaluated at the inside function, and then you're going to multiply that by the derivative of the inside function. So the derivative of whatever this f is with the g of x inside of it, and then you multiply it by the derivative of the g of x. Okay? So let's look at some examples here. Let's say I'm going to use y, and I'm not going to use f of x here because I don't want to confuse with this notation. So let's just say I have y is equal to the sine of, we'll say, x squared. Okay, when you look at this, you need to be able to see that the sine of whatever, that's the outside function. And inside there, you have x squared. So this is like playing the role of f, and this is playing the role of g. So if I'm going to take dy dx, then I'm taking the derivative of sine, which is cosine, but I'm evaluating it at the inside function, x squared. So I'd have cosine of x squared, but then I need to multiply that by the derivative of the inside function, which is just 2x. So it would look like that. So this is the derivative of the composition. So let's try some other examples. Let's say I have, we'll say y is equal to the square root of the tangent of x. Okay, so in this case, the square root function is on the outside, and we could rewrite that as the 1/2 power, right? And so, and inside we have the tangent of x, right? So we basically, our outside is the square root or the 1/2 power, inside is the tangent of x. So if I want to take the derivative with respect to x here, I take the derivative of the outside function, which would be bringing the exponent down, subtracting 1 from the exponent and getting a negative 1/2, but then I'm going to evaluate that at the tangent of x. So it'd be like this, 1/2 tangent of x to the negative 1/2. So that's the derivative of the outside function evaluated at the inside function, and then I got to multiply by the derivative of the inside function. So if you remember back to those rules, the derivative of tangent x is secant squared x. So this would be secant squared x. Okay, so now what you can do is this could be simplified here. This could be brought to the bottom with that 2, and then this could be brought on top. So you could be written like this, and then that 1/2 power would be a square root, but it's the negative is what brings it into the denominator. So you could rewrite it like that. Okay. So let's try another one. Let's say I have, we'll say y is equal to the natural log of, we'll say, x squared plus 1. Okay, so again, on the outside we have the natural log of something, and inside that we have x squared plus 1. Okay. So now, if I take the derivative with respect to x, so I got to take the derivative of the outside function. So the derivative of the natural log is 1 over whatever, 1 over x, if it's a natural log of x. So 1 over whatever, but then I got to put this inside that. So it would be 1 over with this in place of the x times the derivative of this. So times 2x. And then that could be simplified, 2x over x squared plus 1. Okay? So, and the interesting thing about this is a transcendental function, the natural log, and this is a completely algebraic one that you can calculate algebraically, okay, with regular arithmetic operations. So let's look at a few more here. So, let's say we have this. We'll say something like we could say P of t is equal to some population. We'll say like 80 or some amount, like some. This is based on the compound interest formula or something. We'll just say negative 2t or something. So 80 times e to the negative 2t. Okay? So basically you have a constant multiple which just, could come out, and then you have e raised to some power, and then inside of e you have negative 2t. So if I want to do the derivative here, p of t, the constant multiple will just be there, times this, and so that's e raised to some power. Well, the derivative of e to whatever is just e to whatever, okay, so it'll be e raised to this power, to the negative 2t, but then I have to take the derivative of the negative 2t, so it'd be like negative 2, would look like that, and then I could simplify that by saying like negative 160 e to the negative 2t. Okay. So anytime you have something multiplied by the t inside this exponential function, this is you would have to use the chain rule. So even if you had something like y is equal to e to the negative t, right? Well, dy dx would be, this is like e, and then inside you're putting negative t. So this would be the derivative of the outside function, which is e raised to the inside function, which is negative t, times the derivative of the inside function, which is negative 1. This would be negative e to the negative t. Okay, so let me show you now. I want to show you, I'm going to derive a rule that we did earlier where we have like a to the x. Okay, the way that you can derive this rule, if you remember, this was equal to the natural log of a times a to the x, right? So the way that you can do this is you can realize that you can write e or a to the x as follows. You can write it as e natural log of a, and it would be like this thing to the x power. And the reason is, this is the exponent you place on e. The natural log of a is the exponent you place on e to get a. And so basically this here gives you a, and then you raise it to the x power, right? So a to the x can be written like this. But now, if I raise a power to a power, I just multiply the exponents. So I could rewrite this as e natural log of a times x. And so what we have is an outside function of e, and then inside we have natural log of a times x. And natural log of a is just a constant. So this is just like a linear function here, a constant times x. So when I take this derivative here, this is going to be it'll be the derivative of the outside function evaluated at the inside function times the derivative of the inside function. But the derivative of natural log of a times x is just natural log of a. This is a constant times x. So it's just going to be equal to that constant, right? And then e to the natural log of, oh, and this is e to the natural log of a times x. It's that whole thing. Okay, and now this thing goes back to a to the x. So what we really have here is natural log of a times a to the x. That's what this is, the natural log of a to the x. I'm sorry, this whole thing is equal to a to the x. And so basically this is how this rule is derived. But you need the chain rule to derive it, to show it. Okay? So let's try another one. What if I have something like this? Let's say I have y is equal to e times the square root of x squared plus 1. Okay, well, what I have here is I have 3 nested functions. Okay, let me show you. I have e to something. Okay, and that something is this, square root of x squared plus 1. Okay, but this thing here is just, this thing here could be written as the square root of something, and inside of there is x squared plus 1, right? And so maybe I could put these together here like this, e to the something, and inside of there I would have square root of something, and inside of there I would have x squared plus 1. Okay, so I'm putting this inside the square root inside of e. So to take this derivative, we're going to have to peel back. And I'm going to do this one step at a time. You wouldn't have to do this one step at a time, but just to show you what I'm talking about. So I would be doing the derivative of this outside function evaluated at this inside function. Well, the derivative of e to the whatever is e to the whatever, so it'll be e to that. Okay, times the derivative of the inside function. Okay, so now I can pause, and now this is just this chain rule here. So now I'm going to do the chain rule again. I have e to the x squared plus 1. And now to do this chain rule, I'm going to be bringing the half power down. So it would be the half power of, evaluated at this, x squared plus 1. And I subtract 1 from the 1/2 exponent. I get negative 1/2. Okay, but then I got to multiply to get this derivative. I have the derivative of the outside function evaluated at the inside function. Then I got to multiply by the derivative of the inside function, which is just 2 to the x. And so it would be all of this. You could simplify it. I'll just leave it like that. Okay, so let me do a few more here, a few more complicated ones. What if let's say I have this. So let's say I have the, we'll say y is equal to the cosine of, we'll say 1 over the square root of, we'll just say x squared plus 1 again, okay? So it would look like this. So what I can do here, let's see if I can break this down. This would be like cosine of whatever. And you can think of 1 over the square root of whatever as a negative half power. So inside there, I'm putting a negative half power in there. Okay, and inside the negative half power, I'm putting x squared plus 1. So this is how I think of it here. So if you put this inside there, you would get 1 over x squared plus 1. So it's like 3. It's a composition of 3 again. So I would do dy dx of the outside function would be the opposite sign of whatever's on the inside, which is all of this. Okay, times the derivative of the inside function, which I'm going to write like this, x squared plus 1 to the negative 1/2. That's the same as what's in here. And then I can rewrite this derivative here. Let's see. Or I'm sorry, I rewrote it. So then I can I can rewrite what I meant to say is I was confused. I could rewrite this here, and then take the derivative of that, right? That's what I meant to say. Okay, so then when I take the derivative of this, I'm just doing the outside, so that'd be negative 1/2. And then I would evaluate it at the inside, and then subtracting 1 from there gives me negative 3/2. And then I got to take the derivative of the inside function, which would be 2x. And it would look like that. Okay, and then I could do some nice simplifying here. This negative could come out and get rid of that, and this too could get rid of that. So I could write this as sine of 1 over square root of x squared plus 1 times, and then the x I could bring out here, times x, and this would come over, and maybe I'll just keep it as a fractional exponent, x squared plus 1 to the 3/2, like that. And actually, these you could actually combine those, because the bases are the same here. So, oh no, I take it back. Sorry, you can't do that, because this is inside the sine. Okay, so maybe you could finally rewrite this as x sine of 1 over square root of x squared plus 1 all over x squared plus 1 to the 3/2. Something like that. Okay, and you don't have to simplify it this much. Once you've done all this, you've taken the derivative. Okay, so let's try, we're going to try a couple more here. So you could also have something like this. You could have maybe let's say it looked something like this. We'll say y is equal to, we can say, the natural log of x squared times, we'll say, sine of x. Okay, well here you got the natural log on the outside, and then on the inside you have a product of two functions, right? So you're going to need the product rule when you do the inside function. Okay, so dy dx, so I'm taking the derivative of the outside function, which is 1 over whatever, but then I'm evaluating it at that, right? But then I'm multiplying, so this is the derivative of the outside function evaluated at the inside function, and then I'm multiplying it by this derivative, right? And then I have to use the product rule for this derivative, so it would look like this. When I do the product rule, it'd be like 2x times sine x plus x squared times cosine x. Okay, derivative of the first function times the second function plus the first function times the derivative of the second function. And then I suppose you could put this on top. You could have 2x sine x plus x squared cosine x all over x squared sine x. Okay, so it would look something like that. So let me do one more real nice complicated one, huh? let's see here. So I'm going to have y is equal to, I don't know, let's do cosine of, we'll say x cubed minus 1 over square root of, I don't know, we'll do our favorite, x squared plus 1. Something like that. Okay, so basically what I have here is I have an outside function of cosine, right? And in this is placed x cubed minus 1 over square root of x squared plus 1. And so what I'm going to need to do this is the quotient rule. But when I do the quotient rule, I will have to take the derivative of this, in which I'm going to need the chain rule again. Okay? So I have the inside, I have an outside function, and the inside function needs a quotient rule. But when you do the quotient rule, you will have to use the chain rule one more time. So let's see if I can do all of this. Okay? So dy dx, the derivative of the outside function is opposite sign evaluated at the inside function, x cubed minus 1 over square root of x squared plus 1. And now it's times the derivative of this, so I'm going to need the quotient rule. So that's going to be the derivative of the top function, which is 3x squared times the bottom function, x square root of x squared plus 1, and then the top function, so it'll be minus the top, this is the quotient rule, the top function, x cubed minus 1, times the derivative of the bottom function, and this is where I need the chain rule. Okay, so I have the square root on the outside, x squared plus 1 on the inside. So to take the derivative of this, it'll be 1/2 x squared plus 1 to the negative 1/2. And then I have to take the derivative of the inside function, which is 2x. Okay, and then all of this is raised to this squared, right? X squared, the square root of x squared plus 1 squared. So it would look like that. And then there's probably some simplifying you could do in here, like that 2 would get rid of this. You could probably distribute the x amongst this one, get x4 to the 4th minus x or something. You could simplify, but I'm just going to leave it there. So you can see that these can get fairly complicated. But once you get good at doing the rules, then they're like little puzzles where you got to do the right order of operations. So it can actually be kind of fun. If you're, if you've taken a calc class, you could get, like, instead of a book of Sudoku puzzles, you could get a book of interesting derivatives, and you can see if you can find all these different interesting derivatives. So, okay, so that is the chain rule. So there's a few more things we're going to look at.